take a deep breath in.
Right.
Now, let it out. When you do that, it's just incredibly easy to think, okay, I just breathed, I took oxygen in my body, and I pushed carbon dioxide out.
Yeah, it feels like one single, complete, unified action.
Exactly. But what if I told you that the physical act of breathing, like your chest rising and falling, the muscles of your diaphragm contracting, is, well, it's barely even the beginning of the story.
Oh, it really is just the tip of the iceberg.
So today, welcome to our deep dive. We are demystifying the microscopic swap that is happening millions of times inside you right this very second. Because the truth is, the mechanical act of breathing is really just the delivery truck pulling up to the warehouse.
I love that analogy.
Right, the actual unloading of the cargo. Well, that is an entirely different, incredibly delicate process happening on a scale so small, it almost defies belief.
It really is helpful to cleanly separate the physical movement of air from, the cellular reality of keeping you alive. What you're calling the delivery truck, moving air into and out of your airways, that's pulmonary ventilation. Okay.
But the actual unloading of the cargo, that microscopic swap of oxygen for carbon dioxide, is known as external respiration.
External respiration, got it.
Yeah, and that exchange happens exclusively at the boundary between the microscopic air sacs deep in your lungs, which we call alveoli, and your bloodstream.
Right.
And then, much later down the line, you have internal respiration, which is the final step where the blood drops that oxygen off to the tissues and cells throughout your entire body.
Okay, so if the truck is parked at the loading dock of the lungs, how does the cargo actually cross over and get inside the warehouse? Because honestly, for a long time, I pictured the lungs acting like a physical pump.
A lot of people do.
Literally just squeezing and shoving oxygen directly into the bloodstream. And the wild thing is, the top scientists in the world a century ago thought the exact same thing.
They absolutely did. And these were not fringe theorists. We are talking about the absolute titans of early 20th century physiology.
Like who?
Well, you had Christian Bohr, famous for discovering the Bohr effect. Oh, right. Which details how carbon dioxide and pH alter oxygen transport.
Exactly. And you also had John Scott Haldane, a pioneer who developed the first practical stage decompression dive tables for the Royal Navy back in 1907.
Wow, so heavy hitters.
Heavy hitters. Haldane also led massive high-altitude research expeditions. I mean, these were the leading minds of their day. And they looked at their physiological measurements and concluded that the lungs actively secreted oxygen into the blood.
Wait. Secreted, like how the stomach actively secretes digestive acid?
Precisely. Or how a sweat gland pushes out sweat.
Okay, let's unpack this. So they genuinely believe the body spent precious metabolic energy just to move the gases themselves.
Yeah, they believe the lung tissue was an active gland, physically pumping oxygen across the boundary. Bohr's measurements seemed to indicate that the blood leaving the lungs actually had a higher oxygen pressure than the air sitting inside the lungs.
Which would mean?
Which would mean passive diffusion is impossible. Gas won't naturally flow from a low-pressure area to a high-pressure area.
Right, it would be like water flowing uphill.
Exactly. So the secretion theory, this active pumping theory, became the mainstream scientific consensus.
But logically, that would be incredibly inefficient. Spending energy just to acquire the element you need to create energy.
It doesn't make much sense in hindsight, does it?
Not at all. Because it turns out the body spends zero metabolic energy moving the gases themselves. It's a completely passive process. It's like a crowded, high-pressure room spontaneously emptying out into an empty hallway just because someone finally opened the door.
What's fascinating here is the irony of how this was actually discovered. The active secretion theory wasn't overturned by some rival laboratory. It was overturned by Christian Bohr's own student.
Oh, man.
Yeah, a Danish physiologist named August Krogh.
That has to sting, being definitively proven wrong by the person you literally mentored.
Oh, I'm sure it did. But Krogh didn't defeat his mentor with a radically different philosophical argument. He won by engineering vastly superior tools. In 1910, Krogh and his scientific partner, who is actually his wife, Marie Krogh.
Oh, what a power couple.
Totally. They built their own incredibly sensitive gas measurement instruments. They invented a specialized microtonometer that allowed them to measure gas pressures in moving blood with just unprecedented accuracy. And using this new technology, they proved that Bohr's earlier data was fundamentally flawed. It was just a result of measurement errors and experimental artifacts. The Kroghs demonstrated that oxygen uptake in the lung could be entirely explained by passive diffusion.
So the gases simply fall down their own pressure gradients until they reach equilibrium. no energy required.
Right. And Crowe actually won the 1920 Nobel Prize for related work on capillary physiology.
That is just incredible. This vital, life-sustaining process is essentially the body exploiting basic physics for a free ride.
A completely free ride.
But, since there is no active pumping, since the body isn't forcing the issue, it has to rely entirely on the rules of physics to make this passive swap efficient enough to keep us alive.
Which brings us to the mathematical engine governing this whole process.
Right. Fick's law of diffusion. Right.
Adolf Fick was a German physiologist who formalized this law way back in 1855. Originally, he was just describing how dissolved particles move in fluids, but his math perfectly models how respiratory gases cross biological membranes.
Okay, so what does it say?
Well, Fick's law dictates that the rate of passive diffusion depends on a delicate balance of four main physical variables.
Okay, so let's look at the first major physical variable, which is surface area. When we think of our lungs, we usually visualize two big hollow balloons sitting inside our chest.
Right, that's the classic drawing.
But the reality is that your lungs contain roughly 300 to 500 million of those tiny microscopic air sacs, the alveoli.
Millions of them.
Here's where it gets really interesting. If you were to unfold all those tiny sacs and lay their walls out flat, the total gas exchange surface area is roughly the size of a regulation tennis court.
It's massive.
About 70 square meters of surface area, all meticulously folded up and packed into a chest cavity you can wrap your own arms around. It's like trying to clean up a massive water spill in your kitchen. You wouldn't use a flat piece of stiff cardboard.
Yeah.
Right? You'd use a thick, highly textured towel to maximize the actual surface area contacting the liquid.
That is a brilliant way to picture it. The human lung is an absolute masterclass in maximizing surface area within a confined volume, because more surface area means a vastly larger arena for gas molecules to cross, resulting in much faster net diffusion.
Right.
And you can clearly see the importance of this when the surface area is compromised. Take emphysema, for instance, a disease primarily driven by smoking.
Okay.
In emphysema, enzymes called elastases actually chew up and destroy the delicate walls separating those millions of tiny alveoli.
Oh, wow. So the tiny bubbles essentially merge together.
Yeah.
You're losing the fluffy texture of the towel and turning it back into a smooth, flat sheet.
Exactly. That structural destruction slashes the total surface area available for the cargo swap. This is why, in a pulmonary function lab, specialists measure a patient's DLCO, the diffusing capacity of the lung for carbon monoxide. They use a safe, trace amount of carbon monoxide for the test because it binds to blood so strongly that it provides a near-perfect snapshot of pure diffusion capacity.
Oh, interesting.
Yeah, so a patient with severe emphysema might still have the muscular strength to move air in and out. Their physical ventilation might seem okay, but their DLCO number will be drastically reduced because the physical space to make the swap is literally gone.
Got it. Okay, so we have this massive tennis court-sized loading dock. But a massive loading dock doesn't help if the wall between the dock and the trucks is like 10 feet thick, right?
Right.
The gas actually has to cross a physical barrier.
Yes, that barrier is the respiratory membrane. It's the tissue separating the air in your alveoli from the blood flowing in your capillaries. And Fick's law states that the rate of diffusion is inversely proportionate to the thickness of that barrier.
So the thinner the wall, the faster the gas crosses.
Exactly. And the human respiratory membrane is wildly, almost unbelievably thin. We're talking on the order of 0.2 to 0.5 micrometers.
To put that in perspective for everyone, 0.5 micrometers is roughly 1/50th the thickness of a single sheet of tissue paper.
It's hard to even fathom.
That is the only thing keeping you from drowning in your own blood.
It is remarkably delicate, and anything that thickens it directly and immediately slows down that vital gas exchange. For example, if a patient develops heart failure and fluid backs up, flooding the microscopic space between the lung and the blood vessels, the barrier thickens.
Oh, that makes sense.
Or if they develop pulmonary fibrosis and lay down thick scar tissue, again, the barrier thickens. The oxygen simply has to travel too far through the tissue to reach the blood in time.
Okay, that sets us up perfectly for the pressure gradient itself.
Yeah.
How do the gases know which way to go across that ultra-thin wall? Because there has to be a physical push, right?
Right.
Dalton's law tells us that every gas in a mixture acts independently, exerting its own partial pressure. So fresh air sitting down in your alveoli has an oxygen partial pressure, or PO2, of about 100 millimeters of mercury. But the dark, deoxygenated blood arriving at the lungs from the rest of your body has a PO2 of only about 40.
Yes, so you have a high pressure of 100 on the lung side of the membrane and a low pressure of 40 on the blood side. That creates a steep 60-millimeter pressure gradient.
A huge difference.
Yeah, so oxygen behaves like a boulder rolling down a really steep hill. It naturally and rapidly falls down that gradient, crossing from the lungs into the blood until the pressures on both sides equilibrate.
But the body doesn't control the atmosphere. So what happens when you climb a mountain and mess with that atmospheric pressure?
Things change dramatically.
Like, look at the famous 1981 medical expedition to Mount Everest, led by physiologist John West. They literally dragged scientific equipment to the roof of the world to study this exact physics.
It was an incredible undertaking.
And at the summit of Everest, the barometric pressure, the actual weight of the sky pushing down on you, drops to about a third of what it is at sea level. Because there is less pressure pushing the air into your lungs, that alveolar oxygen pressure drops from a healthy 100 all the way down to a suffocating 35.
And suddenly that steep hill just vanishes. Think about it. If the air in your lungs is sitting at a pressure of 35 and the venous blood arriving from your tissues is sitting at 40, you don't have a downward gradient anymore.
Right, the hill is flat, or even slightly uphill.
Exactly. West's expedition demonstrated that at extreme altitudes, healthy human lungs literally become diffusion limited.
Wow.
The physical pressure pushing the gas is just no longer strong enough to drive the oxygen across that tissue paper membrane fast enough to sustain normal human function. It is one of the very few scenarios where the diffusion step itself is the bottleneck for a completely healthy person.
Okay, so we have surface area, membrane thickness, and the pressure gradient. But there's a flaw in the math here when we look at the other half of the swap, which is carbon dioxide.
Let's hear it.
We just established that oxygen needs this massive, steep, 60-point pressure gradient to drive it into the blood. But the blood arriving at the lungs has a carbon dioxide pressure of about 45, while the air sitting in the lungs is at 40.
Right.
That is only a tiny 5-point pressure gradient pushing the toxic CO2 out of the body. How does it ever clear the membrane fast enough with almost no push behind it?
It clears because of the final variable in Fick's law, which is the diffusion coefficient.
Okay, what is that?
It's an intrinsic physical property of each specific gas based on its molecular weight and how easily it dissolves in a liquid or tissue. And carbon dioxide behaves very differently than oxygen.
How so?
CO2 is roughly 20 times more soluble in human tissue than oxygen is.
20 times. So it's like the difference between trying to shove a solid wooden block through a tight doorway versus just pouring a bucket of water through it.
Perfect.
The water just flows. CO2 dissolves and slips through that tissue paper membrane so easily that it simply doesn't need a massive pressure gradient to force it. Its extreme solubility completely makes up for the weak pressure push.
Exactly. But understanding the drastic difference in solubility between those two gases is crucial because it explains what happens when diseases target the respiratory membrane, creating these just terrifying clinical scenarios.
A perfect example is the phenomenon of happy hypoxia, which is often called silent hypoxia.
Yes.
This became widely recognized during the COVID-19 pandemic. Patients were walking into emergency rooms, sitting up in bed, maybe even scrolling on their phones, looking totally comfortable.
Right, seemingly fine.
But when nurses placed a pulse oximeter on their fingers, their oxygen saturation levels were in the 70s or 80%. That is dangerous crash cart territory.
Absolutely critical.
Their tissues were starving for oxygen, but they weren't gasping for air. They weren't breathless. Why weren't they feeling the suffocation?
It comes entirely down to how the SARS-CoV-2 virus interacts with the variables of Fick's law we just talked about.
Okay.
The virus aggressively attacks the alveolar capillary membrane, triggering severe inflammation. Fibrin and fluid flood that microscopic gap.
So the membrane thickens dramatically.
Yes. And oxygen, which we know is not very soluble, suddenly hits this thick, inflamed wall and physically cannot diffuse across it fast enough. The patient's blood oxygen levels plummet, but carbon dioxide...
Carbon dioxide has that massive solubility advantage.
Precisely. Because carbon dioxide is 20 times more soluble, it acts almost like a ghost walking through a wall. It can slip through that thickened, inflamed, fluid-filled membrane just fine.
Why?
The CO2 crosses into the lungs and is exhaled normally. Now here is the crucial physiological twist. The chemoreceptors in your brainstem, the chemical alarms that trigger that terrifying, panicky sensation of breathlessness or suffocation, are primarily tuned to detect a buildup of carbon dioxide, not a drop in oxygen.
So what does this all mean? You're saying the body's emergency alarm system is basically wired to the wrong gauge for this specific disease.
Yes. Because the CO2 was escaping normally, the brain never detected a problem. No alarms rang.
That is wild.
Understanding the basic physics of Fick's law completely demystified a counterintuitive clinical presentation that deeply confused hospital triage protocols early in the pandemic. The oxygen couldn't get in, but because the CO2 could get out, the brain felt completely at peace.
That is terrifying, but it makes perfect mechanical sense. Okay, let's say the gases successfully crossed the membrane, the oxygen made it into the blood, the CO2 made it out. Okay. The journey still isn't over. And I had a massive misconception about this next step. I always pictured my blood acting like a bottle of carbonated water.
You're definitely not alone in that.
I thought the gases just dissolved directly into the plasma and floated around, just fizzy blood carrying the oxygen to my brain.
It is a very common visual, but it's physically impossible. Blood is mostly water, and oxygen is terribly insoluble in water.
Right.
If human beings relied exclusively on dissolved oxygen floating freely in the plasma, our hearts would need to pump an incredibly massive volume of blood. We'd need a resting cardiac output roughly 15 times higher than we currently have just to deliver enough oxygen to stay alive.
15 times higher.
Yeah. In reality, only about 2% of your oxygen travels dissolved in the blood plasma.
2%. So where's the other 98%?
The remaining 98% is carried bound to a specialized iron-rich protein called hemoglobin, which is packed by the millions inside your red blood cells.
Oh, yeah.
Think of the hemoglobin inside the red blood cells as dedicated warehouse workers. The oxygen crosses the loading dock, and these workers immediately grab it and physically carry it deep into the building.
Okay, so oxygen needs these dedicated workers to get inside. Does carbon dioxide use the same workers to get back out, or does it have its own system?
CO2 transport is much more complex, and it's distributed across a few different methods. Only about 7% travels dissolved in the plasma. A substantial chunk, around 20 to 23%, binds directly to the hemoglobin itself, forming a compound called carbaminohemoglobin. But the vast majority of carbon dioxide, roughly 70%, undergoes this fascinating chemical transformation.
What kind of transformation?
An enzyme inside the red blood cells called carbonic anhydrase rapidly converts the CO2 and water into bicarbonate ions and hydrogen ions.
Interesting.
These ions safely travel through the bloodstream until they circulate back to the lungs. Once they reach the lungs, the enzyme runs the reaction in reverse, converting the ions back into CO2 gas, which diffuses across the membrane and is exhaled.
But this extreme reliance on hemoglobin to carry our oxygen creates a massive vulnerability, doesn't it? Because carbon monoxide poisoning completely exploits this transport system. It completely separates the idea of gas crossing the membrane from gas actually being delivered to the body.
That is the truly insidious nature of carbon monoxide, or CO. It is an odorless, colorless gas that diffuses across the respiratory membrane just as easily as oxygen.
So no alarms go off.
None. If you inhale it, there is no problem with physical ventilation and no problem with diffusion. Fick's law is working perfectly.
Okay.
The physiological failure is entirely downstream. Carbon monoxide binds to the iron in your hemoglobin with an affinity roughly 200 to 250 times stronger than oxygen.
Oh, wow.
It essentially hijacks the red blood cells, locking onto the exact binding sites that oxygen desperately needs and refusing to let go.
So relying on a standard pulse oximeter, that little glowing clip they put on your finger at the doctor's office during a carbon monoxide emergency, is deeply flawed.
Very flawed.
It's like counting the seats on a bus through a tinted window, seeing they're all occupied and assuming everything is fine. But you don't realize the seats are taken up by plastic mannequins instead of paying passengers.
That analogy perfectly highlights the technological blind spot. A standard pulse oximeter shines red and infrared light through your finger to measure the percentage of hemoglobin binding sites that are occupied by something.
Just anything.
Right. But a basic model cannot easily distinguish between a passenger and a mannequin, between normal oxyhemoglobin and lethal carboxyhemoglobin. It will happily display a falsely reassuring 99% oxygen saturation, even while the patient's cells are critically suffocating because the carbon monoxide refuses to yield those vital seats.
That brings up a really important clinical dynamic. If a patient is hypoxic, if their tissues are starving for oxygen for whatever reason, the immediate instinct is to put an oxygen mask on their face and crank up the flow.
It's the standard first response.
But is oxygen uptake normally limited by the diffusion process or by the blood flow itself?
If we connect this to the bigger picture, let's look at the mechanics of a healthy lung at rest. Blood spends about 0.75 seconds traveling through a microscopic pulmonary capillary.
Okay, 0.75 seconds.
But the hemoglobin in that blood fully equilibrates, meaning it fills up all its empty seats with the oxygen diffusing from the alveoli in only about 0.25 seconds.
Oh, so the blood is 100% loaded with oxygen in just a third of the time it actually spends parked at the loading dock. It's like a fast food drive-thru where the bag is handed to you before your car even comes to a complete stop.
Exactly. Because of that massive built-in time reserve, healthy lungs are considered perfusion limited at rest. The limiting factor isn't how fast the diffusion happens across the membrane. It's simply how fast the blood, the perfusion, is flowing past to pick it up.
So when do we burn through that reserve?
You only burn through that time reserve and become diffusion limited under extreme physical stress. That could be an elite marathon runner where the heart is pumping blood so incredibly fast that transit time drops below 0.25 seconds. Or it could be extreme altitude where the pressure gradient vanishes. Or it could be a disease that thickens the membrane, slowing down the loading process.
And if a patient has a diffusion problem, like a thickened membrane from pulmonary fibrosis, putting a high-flow oxygen mask on them actually works, right?
It does.
Because you're artificially packing more oxygen molecules into the lungs, increasing the pressure, and making that downhill gradient super steep to force the gas across the thick scar tissue.
Yes, supplemental oxygen works beautifully for overcoming diffusion barriers. But consider a completely different mechanical failure, a scenario called a pure shunt.
A pure shunt.
Imagine a baby born with a ventricular septal defect, which is a literal hole in the muscular wall separating the pumping chambers of the heart. Dark, deoxygenated blood takes a shortcut through that hole, completely bypassing the lungs, and gets pumped directly back out to the body.
Oh, so the delivery truck completely skipped the warehouse. It took a detour.
In that pure shunt scenario, pumping 100% oxygen into the baby's lungs through a mask does virtually nothing for the bypassed blood. You can pack the loading dock with as much cargo as you want, but the blood never drove past it to pick it up.
Right, of course.
Understanding the difference between a diffusion limit and a perfusion shunt is a critical diagnostic distinction for physicians trying to save a failing patient.
It is wild how this invisible, microscopic physics engine dictates exactly how medical professionals treat you in an emergency. And honestly, it dictates every single aspect of your daily life. For you listening right now, this passive, energy-free swap of gases is the foundational reason you are awake, aware, and alive.
Absolutely.
It's the reason why installing carbon monoxide detectors in your hallways is absolutely non-negotiable, because your brain's biological alarms simply will not wake you up.
They really won't.
It explains why elite endurance athletes torture themselves at high altitude to force their physiology to adapt to smaller pressure gradients. And it's why understanding this deep mechanical science literally dictates life and death in the intensive care unit every single day.
It really is the foundational physiological step that makes every other level of complex human function possible. And, as we wrap up, this raises a fascinating evolutionary question.
Oh, I'm intrigued.
Think back to those dyspnea sensors in the brainstem, the chemical alarms that trigger the terrifying, urgent feeling of breathlessness based almost entirely on carbon dioxide buildup rather than oxygen starvation.
Right, the wrong gauge.
If human evolution prioritized a sophisticated alarm system for excess CO2 while leaving us relatively blind to low oxygen, what does that tell us about the ancestral sea-level environments our bodies originally adapted to compared to the high-altitude flights, deep-sea dives, or high-tech modern environments we casually challenge our lungs with today?
Man, that is a thought that will definitely stick with me. We are walking around with ancient hardware trying to navigate an incredibly modern world.
We really are.
So the next time you take a deep breath in and let it out, remember, you're not really breathing. You're just parking the delivery truck. The real miracle is the completely passive, physics-driven cargo swap happening a billion times over, right inside your chest. Keep questioning the incredible machinery hidden inside you, and thanks for joining us on this deep dive.